In this short video, we're going to add one definition and we'll do one example. The definition is a convergent sequence, and forgive me if I've already said that. I probably have many times. We've spoken about a sequence converging, and if it does converge, then it's called a convergent sequence. Sequence AN is convergent if there exists a real number, capital A, such that AN goes to A, converges to A, the real number, as n goes to infinity. And as I've mentioned, sometimes I leave off the as n goes to infinity. It should be there, but I kind of use shorthand sometimes. Now the new term, for sure a new term, is if AN is not convergent, then it's divergent. So a sequence is either convergent or divergent. And I'll just make a quick note. There are a couple of reasons that it could be divergent. One is that we've seen just a few minutes ago in an earlier video that it could be increasing without bound. It's not heading toward it's not honing in on a real number. It goes, so to speak, it goes up to infinity. The other reason is it could be bounded, but it just oscillates back and forth between two numbers, for example. It's not honing in on one particular limit. It just toggles back and forth. Okay, note, if AN converges to A, then A is called the limit of the sequence. And we might write this: A is equal to the limit as n goes to infinity of the ANs. This means that A is the limit of the sequence. This is only true if AN is a convergent sequence, and it converges to this real number A. Well, let's now do an example where we're showing that this is a convergent sequence. Now, it's interesting. When trying to show that a sequence is convergent, what do you need to know? You actually have to know the value that it converges to. If you don't, then we don't know how to prove it converges. So we'll have to guess. This is not a hard guess. This is getting closer and closer to 10. And in fact, I'll even make a note here. We have to know what the limit is in order to prove that it converges to that limit. Okay, so this would be like my AN, as n goes from 1 to infinity. Well, how do we prove things converge? I need to be given an arbitrary epsilon. Let epsilon greater than 0 be given. And all I need to do is come up with the capital N for the definition. Okay, let's let capital N be a natural number. Let it be such that it is bigger than 1 over epsilon. And notice, if epsilon is a tiny number, and we usually think of epsilon as being an extremely small positive number, that means capital N is going to be a very, very large number. So that means, in particular, I'm going to put this in parentheses, this means that epsilon, or 1 over capital N, is less than epsilon. That's why we chose N the way we did. Okay, thus, for all n greater than capital N, what do we have? Well, we have 10 minus 1 over n minus 10. Remember, that's what I have to prove is less than epsilon. The term of the sequence minus the limit. What does that equal to? That is equal to 1 over n, right? Because it's in absolute values. And that's less than 1 over capital N, because little n is a bigger number than capital N, and they're in the denominator. And that's less than epsilon. And we're done with the proof. Just to make a note what this is like AN minus L. Right here. So fairly simple, it took very little algebra.